Hello everyone and welcome to the channel. Today I'm going to talk about compound interest and Euler's number. I hope you'll find the presentation interesting. And okay, so before we begin I have to go over some definitions and theorems. The first one we'll discuss is the limit. So L is the limit of a sequence if for any distance you choose from that limit, you can find an index of the sequence after which any term of the sequence will be at least as close to the limit as you chose. If this is true for any choice of distance, then L is the limit of the sequence. Don't worry if you didn't fully understand it, it's not that important. What's important is that you get a grasp of what this means, and for that purpose I made these figures. So the first figure shows a monotonically descending series that converges to a limit. The second figure shows a monotonically ascending series that converges to a limit. And the third figure demonstrates that a series can be neither ascending or descending and still converge to a limit. The fourth example shows a sequence that diverges. It doesn't have a limit. It's defined as 1 for odd indexes and as -1 for even indexes. Later in the video we'll show a certain sequence converges by showing it that it behaves like the second figure. Okay, the first theorem states that if a sequence is non-descending and bounded from above, then it converges to its supremum. I won't discuss what a supremum is here. The important part is that it converges, and what this theorem means is that if the conditions that are stated are met, then the sequence will look like the second figure from the previous slide. Alright, so the next theorem states that if limit exists, then the sequence is bounded. Third definition is a definition of factorial. Fourth definition is a binomial coefficients. Fifth definition is Newton's binom. Sixth is the sum of a geometric series. Seventh inequality will be used to reach an expression that resembles geometric series later. And the eighth inequality is the averages inequality. That's it. Let's consider the bacteria population growth problem. Assume at time 0 we have one bacteria. After 1 second, this bacteria splits into 2 bacteria. After another second, each of these bacteria splits into 2 bacteria. So we get 4 bacteria and so forth. We get a sequence where each term is twice as large as its predecessor, and a generalized expression for the term in the sequence is written here. Now, the compound interest problem is a generalization of this idea, and it does two things. It gives a freedom degree in the form of an arbitrary interest rate, marked as R here, which is 1 in the bacteria population growth problem. And the second thing is trying to figure out what happens when the growth is continuously happening and not just in discrete time spans. So in order to formulate this problem, consider the following scenario. The bank gives you a loan, right? So now you have a debt to the bank, and every, certain time period, the bank takes a certain percentage R of your debt and adds it to the already existing debt, and this is your new debt. And after set amount of time, this will be your debt. But this still doesn't account for the continuity of the problem. In order to do that, we will take t to be one time span, And we'll take this one time span and split it into n growth cycles, each of which will have r over n interest rate. So what we will get is the following formula. And as mentioned before, to account for the bacteria population growth, we take R to be 1 and T to be 1. So we end up with this expression, this sequence. And if we take n to infinity, meaning we split one time period into infinitely small time periods, we will get what happens when the growth is continuous. So we take n to infinity and see if this sequence converges. Okay, so here I included a reminder of the theorems that will be used, that we discussed earlier. So let's begin. What we're trying to do is find out whether 1 plus 1 over n to the power of n converges. And we're going to do it by using the first theorem. So what we need to do is show that this sequence is non-descending and that it's bounded from above. So we start here from showing that it's bounded from above. So the first thing we'll do is open this expression using Newton's binom, which is number 5, into a sum. And we see that this sum has a lot of factorials in the numerator. And we have a tool to switch these factorials with powers of 2, which is good because it resembles the geometric series sum. So we're going to use number 7 to enlarge the expression, and we end up with line number 2. And this line, in this line, the blue expressions, there are a lot of expressions that cancel out with each other. So we end up with blue expressions that are in the third line. And the green expression here is just switched with 1 over 2. And this is okay because we're taking the limit at infinity, so we can choose an index that is larger than 2, which then means that 1 over n is smaller than 1 over 2. So this is also a valid substitution. So what we're left with is terms that are actually the terms of the geometric series sum, multiplied by expressions that are smaller than 1. It's easy to see that because n is the largest term in the multiplication, so the numerators are larger than the numerators, and the whole expression is smaller than 1. So we can continue to enlarge the expression. And so we end up here with the geometric sum, which we know converges, and therefore it is bounded, and the whole expression is bounded. And here we finished showing that 1 plus 1 over n to the power of n is bounded. All that's left now is showing that the sequence is non-descending, which means showing an is smaller than an plus 1 for all indexes. And we're going to do this using the number 8, the averages inequality, with a clever choice of series. So the series we choose is the first term will be 1, and the other n terms will be 1 plus 1 over n. And once we substitute into number 8, we get these expressions. And here you can see we get an, right? And n plus 1 root of it. And on the other side, we get the the inside of the an plus 1. So if we raise everything to the power of n plus 1, we get exactly what we want. An is smaller than n plus 1, and we finished showing that the sequence is non-descending. So now we use theorem number 1. The sequence is non-descending and bounded from above, therefore the limit exists, and this limit is called E, the Euler's number. You may be familiar with it, and this will be the ratio between the terms of continuous growth instead of 2, that was the case with bacterial growth. This can be further generalized to show the arbitrary interest rate we talked about before, and taking this limit, there's a clever trick here which isn't exactly true, and there's more work to do here to show that this converges, but if you use but the limit is correct, and you can see that this is the definition of the exponential function when you take an arbitrary interest rate. The problem with what's written here is that we used n tilde as n over r, but n over r isn't necessarily a natural number, and what we proved earlier is only true if n is a natural number. So, but this is the correct idea for the proof. You need to use the sandwich law and some manipulations in order to show this limit. You're welcome to try it yourself. If you're interested, I'll make a video about this. Let me know in the comments what do you think about the video, what would you like to hear about next, what did you like, what did you dislike. That's it. Hope you enjoyed it, and see you on the next video.